All right, so welcome back. So in the second lecture, I'm going to talk about graphs and also large language models. So this is the outline of the lecture. First, I'm going to talk about LLMs. So LLMs was, they were a revolution when they arrived. And then there was a question. So LLMs, you remember, replaced RNNs with LSTM. So we, of course, asked the same question. So maybe we don't need any more graph neural networks. And if you have a transformers, that would be enough. So this is what we, the question we ask. This is the research question we ask for. It turns out that you can still use graphs to improve LLM prediction. And I'm going to show you how. Just asking if a lot of people speak, so I just want to know if is everything fine? There's a lot of discussion around, so I just want to know. It's fine. Yes. Are you ready, or do you need more time? I don't know. Ready? Okay. Thank you. Okay, so let's talk about the deep learning revolution. So as I said, everything started with computer vision. So it was in 2012. So at that time, there was ImageNet. So for us, it was really big. There was 1.2 million images. Each image has 224 by 224 pixels. And the CNN that was introduced, the convolutional neural networks, the name was AlexNet, and it has only 8 layers. And only 61 million parameters. So if you use Google Colab, you know that 61 million is nothing. Okay, even if you have 1 GPU from Google, this is something that is nothing. But still, they were able to kick off the deep learning revolution. And also the hardware. The hardware, there was only 2 GPU, actually, only 2 small GPUs with 1.6 teraflops operation. So that was, but still, you know, industry started to work on self-driving cars. Now, if you go to Los Angeles or you go to San Francisco, you will see way more self-driving cars. So it's coming. There is also, yes, for advertisements. So social network company, they wanted to tag people, recognize faces, and then suggest products to get more money. Also surveillance. So this is something very powerful to track in real time people. So, so that was the industry coming from this. Natural language processing, so text, you see that so the revolution for computer vision starting in 2012, it took 1 decade, 10 years, basically to get started the revolution for language, okay? And things are different. So when they started, there was 1.2 million images. Now to get the revolution for text, it's internet, okay? So OpenAI cracked internet English data set. So this is something like 300 billion word tokens, okay? So this is a huge difference compared to 1.2 million images. The architecture, which is quite surprising, is just a decoder-only transformer, okay? So you take the sequence and you predict the next word. That's it. That's the only thing you do. So this is for GPT 3.5, there was 100 layers, but the number of parameters is also significantly higher than CNN. So 165 billion parameters, which is a huge compared to 61 million parameters. So and also the hardware. So here there was only 2 NVIDIA GPUs. Now you need 10,000, and now it's even more, much more, 10,000 NVIDIA V100 GPUs. So 15.7 teraflops. So you know that usually you need, this is a Moore's law. Every decade you multiply by 10 the GPU power, the number of operations. And from this actually started the generative AI industry. Okay, so now it's every day. For example, for coding, probably you are using, I don't know, you have GitHub Copilot, but you have also ChatGPT, you have Gemini, you can also do text summarization, content creation, and you have many applications coming from this generative AI. So this large pre-trained network, they gave a new name. They call it foundation models. Okay, it's just for large-scale pre-trained networks. So the generative AI industry is booming, as you probably know. So there are some proprietary LLMs like GPT, Gemini, Claude, Grok, and so on. But also there was something. So when we started working on LLMs, I was very worried because at that time there was only OpenAI. There was also Claude coming, but all were actually closed. And the only thing you can do is actually to pay this company to give you back the output tokens. So that was, for a researcher, that was very concerning. But eventually, so Yann LeCun at Facebook, he pushed the company to open source the Facebook LLMs. With the name is Llama. You probably heard about this. So now probably it's going to be very different. Yann LeCun left Meta, probably it's going to be proprietary. But still we have a series of LLMs, open source LLMs, Llama, Mistral, Jima, and also of course DeepSeek from China. So something amazing is coming is basically the open source will be from China. And the closed source will be from the US. So this is a very interesting evolution. The architecture is still a transformer, which is amazing. Nothing has changed. Yes, we have a slight improvement inside the transformer architecture, but it's still the same thing. So that's going to be very hard actually to change the architecture from transformer to something else. Probably, but this is where we are. So yeah, some people mentioned rotary positional encoding. The norm is not layer norm anymore. This is called root mean square norm, different stuff. But you see that we still have the same trend. We increase the number of parameters. So there is this scaling law. Probably you heard about scaling laws. The idea is very simple. If you had more compute, more data, your performance will increase. And we don't know why. Okay, this is very surprising. Of course, it cannot be forever like this. There's going to be, a saturation point, and it's probably coming, very soon, sooner than we thought. Okay, the number of hardware. So that was 2 years ago, 20,000. Now I think this is 50,000, even more. So I think NVIDIA talk about, no, not NVIDIA, OpenAI with NVIDIA. They talk about a huge GPU center that will require twice the power of New York City to run. So this is going to be a huge investment in hardware. So for image generation, so also the techniques are quite impressive. You have probably seen that with Banana from Google, but there are other companies started like Midjourney, Stable Diffusion, DALL-E, and so on. So we also have some open source visual models, largely visual models, but they are not as powerful as they are, for example, for Llama or DeepSeek. So there is something very clear is that internet is composed of data which are all linked to each other. So when I mentioned, okay, with my team, we are working on developing new graph neural networks, for different applications, for example, for text prediction. But at some point, then you say, okay, so maybe all graphs are already being seen by transformer, right? So if you look at the web is just, connections between web pages, And inside web pages, you take Wikipedia, for example, you're going to have also connection between Wikipedia web pages. JSON file also gives you connection between documents, web pages as well. So the graph structure is there, okay? And I'm sure that GPT and other techniques, they have seen all the connections already, okay? So I was very worried with my team because, okay, so maybe we don't need graph neural network anymore. We just need a good LLMs to answer graph-related questions. So, yeah, so we had this question. So what we did, basically, so something also important to understand is that graphs have different modalities. So you can consider graph for text, for example, Wikipedia, and knowledge graph as well, question and answer, different. But you also have different graphs in AI for science, for example, in biology, protein, molecule, also in material. All these are different applications. So I'm not going to talk about this here. What I'm going to talk about is what we call text attributed graph, tag. So basically they are, for example, this knowledge graph. So you're going to have a node. The node is going to have, this is an entity, is going to have some word features, maybe describing you know, the node. And then it's going to have connections with other entities. So this is the relationship. And the relationship has some text features, for example, located in. Okay. So I'm going to talk about precisely this because this is where LLM shines. Okay. So what we did, we use an open data set, which is called OGB, which is the largest graph data set developed by the community. And there is one very popular data set, which is called tag, which is called, what's the name? Archive. Okay, so basically, this is a snapshot of archive. So archive, you know, this is the repository of scientific articles. And basically what they did is that they collected, I don't remember when, it was a few years ago, everything from archive in terms of what are the titles, the abstract, and also what they refer to. Okay, so a paper is going to cite other papers. So the citation is basically a link, an edge in the graph. Okay, and the task is very simple. So given we want to know that given an article that we don't know the class. So in archive we have 40 classes such as artificial intelligence, hardware architecture, data structure. We want to know if this article belongs to one, which of the 40 classes this article belongs to. Okay, so this is what you want to do. So there is a leaderboard to do that, and the SOTA technique. So the SOTA technique is this one. So this is the end-to-end language model. So it's not a large one; it's just a small one. So language model plus GNN. And the precision is 76.6%. Okay. So if you are using very simple features for each article, maybe just a bag of words for you know, the most frequent words that you have in the title and the abstract, the performance is just going to be 70%. Okay. Now what we did is that we asked GPT. Okay. So we give GPT the article. Okay. And we ask GPT, among the 40 classes, give me the right class of this article. That's it. Very simple, zero-shot classification. And GPT gave us 73.5%, which is less than the state of the art. So it's also not so good. Do you know why? Okay, so we would expect much, much higher. Why? Larger? Yes, but what is inside the training data? Yes, yes, it's already written. Yes, so data leakage. Okay, so remember this technique. So OGB was released, I don't remember, 5-6 years ago, I don't remember. But GPT was trained later. So it was trained on the whole internet. So it means he has seen this training data before. So if you already seen the test set, you should have very close to 100%. okay? And this is not the case. So we say, okay, so we still have some time to use graph neural network with LLMs. We can still do some stuff to improve, okay? So now the question is, okay, how do we combine the powerful LLM with a GNN? And this is an interesting question. And for this, I'm going to start by reviewing the advantages and also the limitations of both techniques. So LLMs, the strength is they are able to capture the English distribution. So now more and more languages, but English distribution, just by looking at the next word, is doing an amazing job, much better than anyone could predict. Okay, it was trained on a massive data set. Again, this is the large-scale internet, and by the way, we only have one internet. Okay, so this is also how do we produce more training data is a huge open question in research. And the thing also that was amazing is that just by predicting the next word, and then by prompting. Okay, prompting is basically generation will start with a human question. Okay, so so what is the flight from Singapore to Kathmandu? Okay, so this is just me putting this prompt, and then the system will generate the answer itself. Okay, it works very well, much better than we thought. Okay. So the scaling law also is very important. What I said is that so if you are on Google or Elon Musk, it's okay to put billions of dollars in GPU and also collect more data. You will always improve, whatever the technique you are going to use, because transformer is one technique, but it's not the only technique that can scale up and be very good. Actually, you can do relative techniques that will scale the same way. So it's also very important to understand that there is nothing very specific about transformer. This is a very natural architecture that can scale up. So the limitations, so of course, hallucination. So basically generating incorrect answers. And this is exactly what happened with Google. So Google developed transformer, okay, and they also developed some ChatGPT, some insider ChatGPT at Google. But they realized actually that was making a lot of mistakes, okay? And they were worried that if they release the LLM, then people will start doing bad things, and there would be a bad reputation for Google. But it's not like ChatGPT was the first one, okay? There was already some LLMs. Meta also, like 2 months before ChatGPT, they released an LLM, but for the scientific community, not for the general public like ChatGPT. And then, do you know what the scientific community did? They kill it. They kill it because they say, oh, this is something bad. It will generate bad science, and it's going to be bad for the community. So they kill it, basically. 2 months later, ChatGPT was released, and the rest is history. Okay? So the great idea was actually not to trust the researchers. It was actually to trust people outside research to do something with this new tool. Okay, and they started having amazing ideas. Okay, to do summarization. Okay, people use that also. The high school people, they use it for essay. But this is just giving people the ability to use this tool, and people are quite imaginative to find interesting applications. So that was a great idea from OpenAI, not so good for Google. So they still have limited reasoning ability. So I told you what they are able to do, right? So if you stack many layers of transformer attention mechanism, they are able, by doing token matching, to find a trajectory of reasoning to get to the right solution. So it's pretty good. Actually, if you try for coding, if you try for some I would say high school level mathematics, it works very well. Okay, so I really speed up my productivity using this stuff, but there is also a lot of limitations. So one way now is to try to work on the post-processing. So these LLMs, they are able to generate many sequences. But how do you prune the good sequences from the wrong ones? How you do that, for example, for coding or for mathematics, how you would do that? Okay, so this system can generate an infinite number of responses. You ask, how do you derivate a tangent hyperbolic? I don't know, how do you implement CNN in PyTorch? Okay, so how do you prune the correct answers from the bad ones? You need a verifier. Okay, something that is going to check the code. Okay, I'm going to generate some code, but is this code executable, right? How fast it can be executed, okay? And there are also techniques that can check, if the code is actually has the right structure or not, okay? So you can automatize, basically, at some point, which part of the tree of sequences you are going to use, okay? The same also for mathematics. Now, today, there is the best mathematician in the world, which is Terry Tao. He says basically that this technique, this LLM in mathematics, is able to do actually amazing results. So I was very surprised when he said that, but I believe it. I believe him, he's very strong. So it's also going to prune the search space in some sense. So yeah, so this is where we are. So it's when I put that on the slide, limited reasoning abilities, it looks like people are pushing a little more every day. So I don't know how far it will go. It's very hard to predict. We will see. Okay. For the graph reasoning, I'm going to show you what I mean by limited abilities. So today, again, the only way the machine can reason is by using this trajectory of multi-hop reasoning. That's the only way the machine can reason. Okay. So let's say that, so if you have only transformer, the way you do the matching is by using the attention matrix. Okay, so you give a sequence, you have the attention matrix, and then you basically follow, the highest dot product. Now let's say that you have something more. You know that the hops that you can do, they are constrained by Wikipedia, for example. So you have a knowledge graph which you trust. Okay, many experts, review the Wikipedia. So this is something that we trust. So suddenly, what you can do is that you can also do the jumps, but on the graph. And the graph is something that you trust. Okay. So for example, here is the Mona Lisa is in the same city as Alice's friend Bob. Okay. So this is the Mona Lisa. This is Alice, and this is the friend Bob. Okay. So if you use the GNN, what he will do is that he will do multiple hops, okay, multiple jumps until he gets to the solution. This is what he will do. Okay. So now imagine you can mix the power of LLMs with GNNs together to do the right, sequence to get to the solution. Okay. So this is exactly what we would like to do. So limitations is yes. So there is no graph foundation model today because we don't have large-scale graph data set. Okay. So the largest one is OGB. The size is 40 gigabytes compared to ImageNet, which was more than 10 years ago, 150 gigabytes. Okay. So it's very small. And compared to today with internet size, I mean there is no comparison. The other limitation of GNNs is the lack of powerful hardware. Okay, so for transformer, the GPU that we have today is optimal. Okay, this is not the case for GNN. We need sparsity. We don't have fast, sparse linear algebra operations. When you look at the best GNN model, the number of parameters that you need is less than 50 million parameters. You don't need more. You are going to overfit all the rights. Okay, so compared to 500 billion parameters and even more probably that we have today, this is very, very small. So the question is, how do you combine these LLMs with GNNs? Because LLMs is very huge, 500 billion, I'm sorry, it should be billion parameters compared to 50 million parameters for GNN. So today, if Google wants to do a multimodal, a multimodal generative technique, the way that you do is there is not like, you know, an infinite way to do that. So you have a pre-trained model for text, okay? So you have, let's say you have Gemini or ChatGPT, and then you have a pre-trained model for images. And then what you do is that you learn a joint distribution by using an attention mechanism between the two modalities from the pre-trained model, which are frozen. Okay? So you do that, you have a self-attention or a cross-attention layers between your modalities, and then you learn with some training data the joint distribution. Okay, this is how it is done. If you want to, you know, say, okay, I want a picture of, you know, a man riding a horse on the moon, this is how he will do it. Okay. So we have this issue that these LLMs are, I'm trying to think. So we can use the LLMs to improve GNN prediction, which is okay, but it's not so interesting. This is where we started. Or we have the GNN that we can use to force the LLM to decrease the hallucination. Okay, so this is what I told you before. Let's say you have Wikipedia, you trust your Wikipedia data set, and you want to constrain, to force your LLM to use this information to reduce hallucinations. Okay, so maybe I go quickly on the first one. Yes. So this is a technique that what we did is basically, okay. So remember what I did at the beginning was to, okay, I wanted to check if Gemini or ChatGPT was able to find the correct label of, you know, a new article in arXiv. Okay, I wanted to do that. So what I did is that I gave as a prompt the abstract, the title, and then the question. Okay, so what is the class, basically? And I see the answer given by ChatGPT, for example. I have the prediction, and what I do also, I force the system to justify. So basically, give me your reasoning why you answer this class. Okay. So when I do that, which is nice, then what I did is basically, okay, I need a technique to go from sequence, from the abstract, the title, to a vector. And then I'm going to use also the reasoning of ChatGPT from a sequence to a vector, and finally the prediction given by ChatGPT, okay, which is here. Okay. I'm going to use this feature to improve my GNN model to get better, you know, accuracy. So if you use a closed LLM like ChatGPT, you will never have access to the vector representation of the words, okay, of the tokens. So at that time, we didn't know what to do. So what we did was basically to use a small language model. But now what you can do, which is much better, is to use Llama. If you use Llama, you have access to everything. You have access to the output sequence of tokens, but you have also access to the output sequence of vectors. And you can use these vectors, which are rich information of the reasoning of Llama, for example, for the prediction. Okay. So we do that. I'm not going into the detail. It's not so important. And basically, so using this information, so we developed this technique we call tape. Here, this is the total time it needs to train. So, you know, the more on the left, the better. And this is the accuracy. So the higher, the better. Okay. So what we did, so tape was basically our technique, and we were able to get 78%, which was the top of the leaderboard at that time. And this is a very competitive leaderboard. And the thing is, it was very easy to get it just by using the reasoning of this technique. Okay. So now everybody uses that, but it's very boring. Okay. So I'm going to skip that. Oh yeah, something also that we did was interesting is that we have this data leakage. Okay, so we wanted to know is if we use Llama, for example, maybe the answer is already given. So what we did is that we introduced a new Wikipedia data set by looking at the cutoff day of, I think it was Gemini 3.5, and we took everything after. So we know that this is not part of the training set. And basically, the performance is the same. There is no difference. Okay. Okay, now let me introduce what is, I think, the most interesting one. So this is a technique that we call G-retriever, okay? And the idea is, what I told you before is, okay, if you have a graph that you think is trustful, you want to use this graph to improve your LLM prediction, okay, reduce hallucinations. Okay, so what we introduce is the notion of graph tokens. So the idea, large language model, in some sense, the architecture is, we know the architecture, okay? So we have, let's say, 100 layers of block transformers. Okay, so in block transformers, you have your attention mechanism followed by an MLP, and then you have 100 layers of that. Okay, so this is where you get the, the trajectory of pairwise matching. Okay. The input is more interesting. The input is basically, so if you have some text, for example, here I have, what is the name of Justin Bieber's brother? Okay, so this is the question. So this will be transformed into word embedding, right? So we have, let's say we have the query. The query will go through a word embedding. So basically, you want to represent your discrete word by one vector of d-dimensional, of d dimensions, all right? And this is given to your 100 layer of LLMs, where it does the reasoning, okay? At the end, it will go to the answer. So the answer will be generated one token at a time. You know this is autoregressive, okay? And the answer will be compared with the ground truth that we know, okay? So if we know the ground truth, we know the prediction, we can use cross entropy as the loss, and then backpropagation to update the system, okay, to get the best possible prediction, okay? So this part is standard. This is regular transformer when you do ChatGPT, okay? So what we wanted to do is to say, okay, we have a graph. Can we introduce more tokens? So it's kind of a prompt, but using graph information. So can we transform the graph into a graph token that we also give to the 100 layers of LLMs? You see my point? So today, we are using word token, but maybe that would be good to use also the graph token, okay? So this is exactly what the work is about. So we are going to, okay, maybe I'm going into the details. So we're going to have a graph related to the question. So what is the name of Justin Bieber's brother? So this graph will be, I'm going to show you, will be extracted from a knowledge graph, okay? But we want just the part which is related to the question, which is meaningful to the question, okay? And I'm going to do something else, textualization of the graph, but I will come back to that. Okay. So to get the graph token, this is not something new. Okay, I'm just introducing a new vocabulary, which is a graph token, but that's it. So how you get it is very standard. You can use, for example, a graph transformer or your GNN that you like. You take your graph, you get the node after L layers of GNN. What you compute, you get node features, and then you compute the mean of these node vectors, okay? And this gives you basically one vector that is going to be your graph token, okay? Something else also that we want to do is LLMs are very good with text. So maybe what we should do is that we should represent the text, the graph information with text, okay? So we call this operation textualization. So let's say we have this graph, okay? And then we can textualize a graph saying that a graph G is a set of directed edges defined by ij, where node I points to node j. The graph J is defined with edges 0, 4, 1, 6, and so on and so on, okay? So I have a one-to-one correspondence between this topology and this text, okay? The problem with that is we have no equivariance with respect to the choice of textualization. It means basically that there are multiple ways to represent a graph with text. And we don't know which one is the best for the LLM. We have no idea. Okay? And the performance is going to change. The other issue is, if you have Wikipedia, this is a very big graph, right? So you cannot basically textualize Wikipedia and then put it as a prompt. You will never have enough context window to do that. Okay, so the scalability issue is important. Hallucination, of course. Okay, so what we propose is something that we call graph RAG, okay, which is an extension of RAG. Do you know RAG, Retrieval Augmented Generation? Perfect. Okay, so you know how this ChatGPT and this Gemini works basically. So you prompt something, and what's going to do is that it's going to transform your prompt into one vector, and it's going to look at this huge data set. So maybe one point of the data set is a page, which is represented by one vector, and it's going to do the dot product with all the documents in its database. It's going to retrieve maybe the top 10 documents, and it's going to concatenate the top 10 documents with your query. And then it will ask the LLM to generate. This is today the standard practice for all this LLM stuff. So what we want to do is basically, we want to do not RAG, but graph RAG. Okay, retrieve a graph and give the information of the graph to the query. So how we do that? So the first thing is, let's say we have a huge graph knowledge. What we're going to do first is that we are going to take the node text feature, the edge text feature, and represent everything with one vector. Okay, we just use your favorite, large language model or language model to do that, and you store everything in your vectorial database. Okay, so today there are many databases to do that very efficiently. Okay. Then you ask the question, what is the name of Justin Bieber? So it will go through the language model, have one vector, and then it will do the dot product between this query and all the nodes and edges in the database. Okay? And it will retrieve that. The problem is still big. So what we decided to do is to sparsify the graph. So there are many ways to sparsify the graph, meaning reducing the number of nodes and the number of edges. Maybe I don't need to go too much into the details, but this is something you can do in linear time. Okay, this is if you have been to a course on algorithm, this is one of these algorithms. Okay, so I'm going to skip that. So at the end, you have the graph database, and you extract a subgraph which is relevant to your query. Okay. All right. So we can add the tokens, right? So we're going to have here the graph token, and here we are going to concatenate to the question the textualization of the graph together, okay? So we just add, graph token and textualize graph token here, okay? So, okay, for this also we decided to, because there was no good graph reasoning data sets, so we decided to introduce three benchmarks to do that. That is used now by the community. Okay. What we can show is that this technique improves, if you just use zero-shot, classification, if you use, different techniques, it's always going to be, it's always going to give you the right solution. So the part which is also interesting is the hallucination. So we get actually reduced by hallucination by a significant percentage. Yeah. So in conclusion, so I like this timeline of recommender systems. So recommender system, they started with Yahoo a long time ago, in '98. But the way it was done is basically there was humans that look at the web page and then decided to rank the web page. So it was done by manual annotation. So that was not something that can scale up to, internet. So at that time, that was, internet was much smaller, but still it was growing very, very fast. So PageRank was introduced. You probably know about PageRank. So this is a way to know so you're only looking at the topology of the graph, okay? So if you have one web page which has a lot of connections, it means that this web page is important, and the rank of this web page should be much higher, okay? So you can do that, but the only thing, you are not using any information of text if you use PageRank, okay? Still, Google was very happy with that. Then there was RankBrain, introduced in 2015, and this is work2vec, basically. This is work2vec introduced. Then there was BERT. BERT was, language model based on transformer. It was not at the scale of OpenAI ChatGPT, but that was something useful for Google. And then there was RAG, exactly what I discussed before. So the idea was you can use a large language model. Okay, you prompt and you look at in your database which are the most related documents to that. So this way you can put in context much more related informations. Gemini now that we have. And the idea here is just to add the graph RAG information. So if you have, again, some graph structure that you would like to leverage, this is something you can do by using the GRetriever. Okay, so again, so we have also, I didn't have time to talk about graph transformer this morning, but this is something you can, Vijaya has a very good blog post about this, also Xiaoxing. She has a very good blog post about this, and I recommend you to look at it. Okay, so of course, this can be extended. Okay, so here we only use the word token, the graph token, but there is nothing that can stop you to use the visual token. So you can take a visual transformer. A visual transformer, what it does is basically take an image, it cut the image into patches of the same size, it take each patch, embed into one vector, okay, and once you have the vectors, you can give that to a transformer. Okay, a transformer is agnostic of what was at the input as long as they are vectors. Okay, so you can do that. You can have for each token, each patch token, you can also have something where you can add your visual tokens. So basically, this is, I think, where we are going in terms of multimodality. The input of your LLM is still the most powerful one. So what you want is basically to give as an input your visual token, text token, graph token, and then what you do here, you are doing, it's not really written, but what you are doing is that there is a projection in a linear space where you align the vectors together, okay? Because the information coming from vision or coming from text, they are not aligned. So you need to find a way, and you do that by fine-tuning. You basically need to find a way to align the vectors. This is something that is done, for example, here you see projection. This is exactly what it's doing. It's trying to align the vector space, basically. And I was very skeptical about this, but actually it works very, very well, okay? So, yes. And that's it. Thank you very much. The first question is the hardest.
Congratulations on the paper, and GRetriever is a very popular paper I've seen before as well. So, what type are you going to replace Google search with that?
So that can be an idea of a startup, of course. But yes, I mean, the idea is already taken by NVIDIA. NVIDIA has, so they find, of course, because GRetriever was the first version of this idea of graph RAG. So NVIDIA has already a better version of this. So it's already done in some sense. So now the question is the data set. You need to get access to a lot of graph data set to use this technique. And as I said, it's not like, if you look at internet, it's very easy to scrap, but it's very hard to scrap in a clean way that you are going to extract the correct graph structure. So this is another engineering open problem that we need to solve if we want to do a good startup on this.
To extract the knowledge graph from it.
Yes, exactly. It's everywhere on the internet. It just is very hard to, to scrap.
Thank you.
Thank you. Yes, please.
So, industry, they are spending millions and billions of dollars in LLMs and very small amount of money in GNNs, right? So, is it the future all about combining LLMs and GNNs, or is it about replacing GNN by LLMs for graph reasoning tasks?
That's a very good question. So maybe this is what I started when I said this morning. You know, when I started, transformer is today the best technique as long as you have enough training data set. So if you have enough, I would guess it will replace CNN, it would replace GNN. The problem is that no, it's always very hard to have enough data set. So this knowledge graph, they are actually everywhere in biology, in also if you are like Amazon, if you are like Google. So this knowledge graph, they are everywhere because this is humans putting in the machine, you know, some knowledge that they think are already true. Okay, so forcing the LLM today, it's a kind of regularization process. So you force the LLM to use this knowledge. Okay, the LLM has two things, right? It has the reasoning core and it has a memory core as well. The memory core is not very strong. That's why RAG today is actually pretty good. This is the same with knowledge graph. If you have a good knowledge graph, you would like to help the memory of your LLMs to reason better. That's the idea. So now at the end of the day, the problem in industry is more engineering. So I would say that, yeah, and yes, it's something to decide. Yeah, I have no idea.
Yeah,
Thank you. There is one, I'm sorry, maybe just a follow-up. There is one startup in the US by Yuri Leskovec at Stanford, which is called Kumo, that is exactly trying to do that. And I think they adapted a GRetriever to do exactly this. Again, it's only one startup, so it's never a good sign. It should be a lot.